just want us to have some kind of revision for circle theorem. So first and foremost, we must know what a circle is and the properties of a circle. So a straight line from the center of the circle and touching any circumference is called a radius. And also we have a diameter. As in the diameter is a chord that passes through the center of the circle and touches 2 points on the circumference. So when you have the diameter, we also have quadrant. This is a quadrant. And this is the arc. This is the arc of the circle. We also have another. When you have this is a chord, a straight line touching 2 parts of the circumference, touching the circumference at 2 points, but does not pass through the center. And the chord, this chord divides this circle into 2 major parts. It divides it into a minor segment and major segments. Of course, we know that this is the minor arc and this is the major arc. Then we also have another one which we call the sector. The sector is an arc bounded by 2 radii. You have a radius there, another radius there. So it subtends an angle of theta at the center of the circle. So if we have understood this, so let's quickly go to the theorems, the circle theorems, and solve some examples on each of the theorems. The first one we're going to start with is, okay, let's say theorems now. Number 1, the first one, when you have a chord, or let me see, a line passing through a line from the center of the circle bisects a chord. When we talk about bisect, it means it cuts the chord into 2 equal parts. That is, if I'm going to draw this diagram, that means that a line from the center of this circle, this is the chord. When this chord meets with this line here, it divides this line into 2 equal halves. So that means this part, so I have A, B here, this is my O, and this is M. So in this case, I can say AM equals to MB. So line AM equals to line MB. And this is one of the first theorem that we have to understand, that whenever a line passes, coming from the center of the circle, it bisects the chord. So when we say it bisects the chord, so it means then corollary of this, we can also say that the angle formed by this line that meets this chord, the angle formed is a perpendicular angle. That is, it's 90 degrees. So, let me quickly make a rough sketch of that. Okay, so the angle which trying to equal chords of a circle are equidistant from the center from the center. That's this one that I've explained. And also we can say that the line joining the center to the midpoint of the circle is perpendicular to the chord. So we can say this is the corollary. So the B part of this, the angle formed by a chord, the angle or the line joining the center, the line, let's say the line joining the center of a joining the center to a chord is perpendicular to the chord, that is at 90 degrees. So we can now say angle at OME equals to angle at OMB, so which is equals to 90 degrees. So let us find some questions under this. Well, we may not quickly to take some questions because we need to add some other theorems together. So these theorems that we're going to add together will give us more insight into how to solve problems on tangent. Okay. Circle theorem. Sorry, I'm trying to look for some questions. Okay, so number one question, let's take this. A chord, example, a chord of a circle is 12 centimeters long. So, example now, a chord of a circle, so chord length. A chord of a circle is 12 centimeters long. 12 centimeters long. The radius of the circle is 10 centimeters. The radius is 10 centimeters. Calculate the distance of the midpoint. So we are looking at for the distance of the midpoint of the chord from the center. Calculate the distance of the midpoint from the center of the circle. So we are looking for OM. OM is what we are looking for. So in this case, you can just draw the diagram for emphasis sake. So you have what? We are told that the chord length is 12 centimeters. So since it's 12 centimeters and a line is coming from the center of the circle and dividing this into two equal halves. So we have a 6 centimeters here, 6 centimeters here. And the radius, we are told that the radius of the circle is 10 centimeters. If the radius of the circle is 10 centimeters, then we can now bring out this. What we are looking for here in this question is OM. So we have AB here. So we're going to bring out this. You bring out this. So this is 10 centimeters, this is 6 centimeters. Then we're looking for this length OM. OMB. So we're going to make use of Pythagoras theorem. Using Pythagoras theorem. So we're going to have what? 10 squared equals to, let's call that please OM squared plus MB squared. That's 6 squared. So OM squared will definitely give us 10 squared. Bring this one to this side. We have 6 squared. And that gives us 100 minus 36, which is equals to 64. So OM equals to square root of 64, which is 8 centimeters. So the length of the line from the center of the circle to the chord is actually 8 centimeters. Another way the question can come out is calculate the length of a chord. So example 2, calculate the length of a chord. So let's take our chord length as AB. So calculate the length of the chord AB of a circle of radius 26 centimeter. The circle is having radius of 26, that's OB, which is OB, or OA, which is the same thing. So 26 centimeters. If the chord is 10 centimeters from the center of the circle, so OM, the chord is 10 centimeters from the center of the circle. So 10 centimeters from the center of the circle. So in this case, we can draw the diagram so that you can be able to understand it properly. We have this, the length AB is what we are looking for, and we have R given to us as 26 centimeters. Then this line OM, this OM is given to us as 10. So let's bring it out. We have 26 centimeters, we have 10 centimeters here, and we are looking for AM. Let's call this AM. So AM, using Pythagoras, AM squared equals to, let's call this OM squared minus OA squared. So what is AM squared? We have OM squared as 10 centimeter, and this is this 26. Pardon. Then we have 10 squared. 26 squares gives us 676 minus 100, and this gives us 576. So we're going to look for AM square root of 576, and that will give us 24 centimeters. We have only found the length of AM, but actually what we're looking for is AB. So AB equals to 2 times AM, and that is equals to 22 times 24. You have to show these things, and that will give us 48 centimeters. So the length of the chord is actually 48 centimeters. Someone might put 24 in it and think he has gotten the answer. No, you have not gotten the answer. Please always write the reason what you are doing. Pythagoras, when we are solving second theorem, is better for everything you are doing, make sure you are giving the reasons for your answer. Let's move to the second theorem. The second theorem that I'll be dealing with, that is angle in a circle. So theorem 2, let's call it T2. The angle that an arc of a circle subtends, the angle that an arc of a circle subtends at the center is twice that which it subtends at the circumference, at any point on the circumference. On the circumference. So if we have to draw this diagram, we have let's draw this, and we have a line here, we have this here, this is the center of the, and this joins this to this. We have A, B here, and we have P here. Let's join this. We are going to have S2 here, and X1 here, Y2 here, Y1 here, and this is our center O. and these are points Q. Our points Q, let's call this point Q. So actually what we want to prove here is we want to prove that AOB, angle at AOB, is O, point O, equals to 2 times angle at APB. So the angle that this subtends at the circumference, we want to prove that it equals to twice the angle is sustained at the circumference. So to prove that, we have been able to join P to O to Q. We have extended that. So, and we know that OA, line OA is the same thing as OB, and that's our radius. So the radii, I'm giving the reasons. You must make sure you give the reasons for any of these rules that you are mentioning. So if that is the case, then we can say that looking at this, x1 equals to x2, because these are the this is a radius and this is also a radius. So look at it, this line is equal to this line. So OA equals to, so we can also say that OA equals to OP equals to OB. Let's just note that radii. It then means that S1 equals to S2. These are base angles of isosceles triangle. Base angles of isosceles triangle. So if you have noted that, so we cannot say that there is a theorem in triangle that we know, that we need to know, that the angle, so the exterior angle of a triangle equals to the two opposite interior angles. So we can say that this angle here at AOQ equals to x1 plus x2. If that is taken, so OAQ equals to x1 plus x2, exterior angle, so I'll write exterior angle of a triangle. Then we can also say, that means this is equal to, since this and this are equal, we can just say 2x. This angle equals to 2x. Now, similarly, BOQ, this BOQ is same thing as what? Y1 plus Y2. Same thing as exterior angle of a triangle. And that will give us Y, 2y. So, or we can just write 2y squared, 2y2, x2, x3. So in this case, and our angle AOB equals to, angle at AOB equals to 2. It equals to AOQ plus AOQ angle at AOQ and BOQ, and this equals to 2. We have 2x2 plus 2y2. So we can bring out the 2x. We have 2x2, y2. From here, we can see that x2 plus y2 actually the angle of, so 2 times APB. So AOB equals to 2 times APB. So we have been able to prove that. I am not going to go too deep into this. Let's solve some questions. Let's look at a question here. Let's come to this side. So a question, so you will see lots of diagrams in your exam. You must be able to identify which theorem to use, and you must be able to also tell state the theorem that you are making use of in your solution, so that you can be able to, okay, let's see this diagram. this diagram having one at the center. So we have x here, and we have another one, y here, and we have z, this, (33 degrees). W is here, O is here, X, Y, Z. So from this, the angle subtended, we can see that if you look at this diagram very well, this is the only angle subtended at the circumference of this circle. So what we do here is that, let's note it, this is the angle subtended at the circumference of the circle. The arc that sustains this is the minor arc XZ. So XZ, arc XZ subtends angle XWZ at circumference, and angle XOZ at the center. You can see, look at this angle, correspond with this, correspond with this. So in this case, we can say that XOZ is equal to 2 times angle at XWZ, and that will give us, so we can write it as angle at center equals to 2. Angle at center equals 2 times angle at circumference. This is very important for you to write when you are solving circle theorem. If you don't write these reasons, you might lose some marks, about 2 marks for not writing it. So now in this case, we have 2 times 33 degrees, and that will give us 66 degrees. Now we are also told to look for, okay, the question says find XOZ, which we have just found, and we have to find reflex XOZ. This is reflex XOZ. This is XOZ. This is reflex. I hope you know that we have different types of angles. We have the acute angle. Like this is less than 90 degrees, so it's an acute angle. We have obtuse angle. Once it's more than 90 degrees, that's obtuse angle. Once it's more than 180 degrees, it becomes, we call it a reflex angle. So the remaining side here is what we are told to look for. And in that case, how do we find reflex XOZ is equals to 360 minus XOZ, and that is called, your reason is angle at center. Angle at center, or angle at a point. So angle at a point, let us write as angle at a point. Angle at a point. So this, with this we just write 360 minus 66 degrees, and this will give us 254 degrees, and that's 294. Sorry, 294. 294. We are looking for, we have found the reflex XO. I think we can also look for the angle X. Let's find XYZ. This XYZ, so the reflex angle is in line with this. You can see the way it is. So it is this arc that subtended reflex XOZ at the center, and also subtended this angle XYZ at the circumference. So in that case, we're going to say that XYZ equals to half of the angle at reflex XOZ. This reason is angle at center equals 2 times angle at circumference. So these are how to solve questions of this type. A wire question. Let us take one wire question of this type. The wire question says, let's draw the diagram first. Can I get the calculator? Can I get the calculator? So this question says in this figure above, PQR are points on a circle with center O. If OPQ, okay, this O, this P, no, this P here, and this R, and this Q. If OPQ equals to 36 degrees, what is the size of PRQ? This is a wire question. So in this case, solving this involves so many other things. Now the first thing that we have to note is this angle P. So we tell them, you let them know that, okay, angle OPQ is the same thing as angle OQP, which is the same thing as 36 degrees. You tell them the reason, and that is base angles of isosceles triangle. Base angles of isosceles triangle. In that case, so we already know that this base is 36 and this part is also 36. Then we are looking for POQ. So therefore, angle at POQ equals to 180 minus 2 times 36. Because we have, okay, let me just write it the visual way. So we can say that OPQ, angle at OPQ, plus angle at OQP, plus angle at POQ equals to 180 degrees. You have to tell them the reason. Sum of angles in a triangle. Sum of angles in a triangle. So we have OPQ. OPQ is 36 plus OQP 36 plus POQ is what we are looking for, and this is 180 degrees. So POQ equals to 180 minus 72, and that should give us 108 degrees. POQ is 108 degrees. But this is not the final question that we are asked to look for. We are told to look for PRQ. And in getting PRQ is the angle subtended at the circumference of the circle. So what we need to use the theorem 2 and tell them that what? PRQ is half of POQ. Then you tell them the reason. Angle at circumference at center equals 2 times angle at circumference. I'm always saying this is very important for you to write when you are solving circle theorem. So in that case, we have this equals to half times 108, and that should give us 54 degrees. And that's all that they have asked us to do. Another thing that let's move to another theorem, theorem 3. We'll just take some questions. Angles in the same segment are equal. Angles in the same segment are equal. So we have a diagram of this, right? These are point 0, these are A, these are B, these are P, these are Q. And this, let's call this angle here X1, and let's call this angle S2. So, what we need to do here, if we look at this very well, this is just replication of this. The angle formed, so we can say APB equals half, or let's say AOB equals 2 times angle at APB. AOB is same thing as 2 times angle at what? AQB. And these reasons are for what? Angle at center equals 2 times angle at circumference. If that is the case, then so we can actually say this is what? AOB is the same thing as 2S1. AOB is the same thing as what? 2S2. And that means that 2S1 equals to 2S2. If 2S1 equals to 2S2, the two will cancel each other. Then we can then say S1 equals to S2. So S1 equals to S2. Therefore, we can now say that APB equals to AQB. This angle at angle in the same segment. Can you see from this diagram? You can see this like a chord. This chord divides this into minor segment and major segment. These two angles are in the major segment. Therefore, since they are subtended by the same arc, they are equal. So S1 equals to X2, and that's how to solve such questions. So then let's take another theorem so that we can join them together. And the theorem is, let me make it on another marker. Well, before I go there, let's look at this diagram. A, B, C, D. No matter the number of angles in the same segment, we will always arrive at A equals to B equals to C equals to D, because they are all angles in the same segment. So equals to dot dot dot. Now let's go to the next theorem, theorem 4, which says that angle in a semicircle. Angle in a semicircle. So, and that means that when you have this diagram, if this is the center of the circle, if the semicircle subtends an angle at the circumference, this angle here is angle 90 degrees. And how do we go about this? We have this center as O, this A, B, and this is X. Now, from here we can determine that this angle subtended by this arc at the center is actually 180. So angle AOB equals to 2 times angle at AXB, and that is angle at center equals twice angle at circumference. So if this angle is 180 degrees, and we have, okay, let me write that this, but AOB equals 180 degrees. Therefore, AXB equals 180 divided by 2, which is 90 degrees. So angle in a semicircle is a right angle. The angle subtended by a semicircle is a right angle. I didn't complete it before. So let's take a question. Let's take a question. An example now. PM, this is N, and this goes to this place Q, this joins with this, and this goes back to Q, P here, and this point is noted at D. Once you see these dots and O, it makes it the center of this circle. So from here we have M here, we have P here, we have N here, we have Q here, and O here, and this place was noted as 63 degrees. So we are told to find Q and M in this question. Number one thing that we need to note is this triangle PQM, triangle PQM Sorry for the break in transmission. So let's quickly look at this question again. So we are told to find QNN from this diagram. So let's go to this part of the board. We need to realize that that center O really will help us to understand how to solve this question. No matter how big the question is, the moment you can identify some particular theorems. Now look at this question. We have POM, that's the diameter, and it's subtending an angle at the circumference, which is PMQ. Therefore, I will write solution PMQ, angle at PMQ equals to 90 degrees. Immediately you write that, you must also follow it with the reason. This we call essential reasons. Omission of this will lead to -2 marks in your calculation. So now for this I'll write angle in a semicircle. Angle in a semicircle is 90 degrees. So if this place is 90 degrees, then we need to find MPQ. So let's say MPQ plus PMQ plus PQN equals to 180 degrees. And this is angle, sum of angles in triangle. We are MPQ is what we're looking for. MPQ plus this is PMQ 90 plus 63 equals to 180 degrees. So MPQ plus let's say this is 3 and 153 equals 180 degrees. So MPQ equals 180 minus 153, and that will give us 7 and 27 degrees. 27 degrees, and that is not what we are told to look for. We are still looking for QNN. 27 degrees is MPQ, the angle at MPQ. But note that this MPQ is the same angle is being subtended by arc MQ, and this arc MQ also subtends an angle at the circumference, which is what? MNQNM or MNQ, anyhow you call it. QNM, that's the way it was given to us. So, and from the law that we have, the theorem, angles in the same segment are equal. Therefore, we are going to write that angle QNM equals to angle MPQ equals to 27 degrees. Then you tell them the reason. Angles in same segments are equal. And that's the solution to that question. Let's move on to another theorem. Cyclic. When we talk about cyclic quadrilaterals, you must understand what we mean by cyclic quadrilaterals. Look at these two diagrams. PQRS, and look at this diagram. OPQR. These two diagrams are different. This is a cyclic quadrilateral because it's having all the vertices touching the circumference of the circle. Why this is just a normal quadrilateral in the circle? It is not having the last part is not touching the circumference of the circle. So we cannot refer the second diagram as a cyclic quadrilateral because one of the vertices is not touching the center of the circle. And so when we are dealing with cyclic quadrilaterals, we have to note, so the angles in opposite segments are, so okay, angles Opposite angles of a cyclic quadrilateral are supplementary. So we can say this theorem 5. How do we put it? The opposite angles. The opposite angles of a cyclic quadrilateral are supplementary. This means that what? We can say P Q R plus PSR equals 180 degrees. QPS plus QRS equals 180 degrees. The meaning of this is opposite angles. These are the opposite angles. This opposite to this. This opposite to this. When you add this and this, it must give you 180. If you add this to this, it will surely give you 180. And that's the major thing you need to understand with the cyclic quadrilaterals. But let me show how we got that to be so. So let's draw the diagram and let's understand it the way this one is better. Okay, so we want to prove, let's look at the diagram here. We have a diagram. This is D, this is A, this is B, and this is a C. We are taking it to the center. Center O, and this is 2x, this is 2y. If this is 2x, this is x, and this is y. We already understood that from our previous theorem, which is that angle at circumference equals to twice the angle at the circumference. Angle at center equals to twice angle at the circumference. So from here, we want to prove that BAD, angle at BAD plus angle at BCD equals 180 degrees. And these are cyclic quadrilaterals, so we want to prove it. So the first thing, we have noted that BOD, angle at BOD equals 2y. Angle at reflex BOD2. Reflex BOD equals to 2x. And these are angles at the center. Angles at center is twice angle at circumference. Okay, so in this case, when you add this to y plus 2x equals to 360 degrees at a point. Okay, so I think I need to change the marker. Okay, so we have been able to let me change this marker. It's not working well. So if 2y, so we can bring this together. Y plus x equals to 360. Therefore, 2 we cancel this. We have y plus x equals to 1. Our y equals to the y angle y is DBCD, and the x. See, our angle y is actually the BCD plus x is the BAD, which equals to 180 degrees. So hence we have proved that we have been able to prove. So prove the fact that we said that opposite angles of a cyclic quadrilateral are supplementary. So let's move to let's solve some questions on that. If we can find, let me see if we can find one that is technical. Okay, let's see this question. Example. We have a diagram. A, B, say please can you stop the discussion? A, B, C. We have angle E here, and this D here, this C, this A, this 127 degrees, and we are looking for, so we are told to find, remember this point here is the center of the circle. Once you see this point, it means center of the circle. We are told to find, so we are told that CE is the diameter of a circle. There is circle A, B, C, D, E. If ABC is 127 degrees, find ACE. So we have a question here where we are told to find the angle at ACE. Given that in that case I can actually get something here. It means that the angle here, this total angle here. So let's solve it. Angle at CDE is 90 degrees. This angle in a semicircle. That has been solved, but we know that the angle here is actually an opposite angle to this BC. So ADC is different from ACE. ADC is equals to 180 minus 127 degrees, and this is angle, opposite angles of cyclic quadrilateral, and that will give us this 3 and that 53 degrees. ADC, angle at ADC, so this place is 53 degrees. If that place is 53 degrees, then we can actually get this side here. because this angle here this is 90 and this is 53 degrees, and we're looking for this angle. Then we can say that we have found EDC or EDC is 90 degrees. We have found that already, which we also wrote as CDE as 90 degrees. We have found ADC. This is the ADC. And we're looking for ACE. Now, if we look at this very well, the angle here, the remaining part of this angle is 90 minus 53. So angle ACE, so we can write ACE. Angle AC, AD. Angle A, no, not A now. This side is 90, this whole thing is 90, so this side here is EBC. EBC is 90 minus 53. So, and that is what 27 degrees. The 37 degrees, sorry, 37 degrees. And then, so we have been able to find this angle here. This angle, if you look at it very well, this AE is the arc AE. Arc AE subtends angle ATE at the circumference, and also subtends angle ACE at C. So therefore, we can say that angle ACE equals to angle ADE, which equals to 37 degrees. And this is what angles in same segments. Very simple. I think with this we have been able to touch the major theorems. The next one we'll be talking about in our next class will be the second theorem, geometry 2, which is on tangent. See you in the next class. Stay tuned.